Okay, this video is the presentation for 1.5 on conditional statements. And so our first slide on conditional statements. A conditional statement, for one thing, is got two parts to it. There's an if part and there's a then part. We call the then part the conclusion. And we call the if part the hypothesis. There's a notation that goes with this. We let P stand for hypothesis, and then we have a right-hand pointing arrow and a Q for the conclusion. And we read this as P implies Q, or if P, then Q. So the P is like a variable. It stands for whatever the hypothesis phrase is, and the Q is another variable that stands for whatever the conclusion is, and they're separated by an if. Well, they start with an if and they're separated by a then. So let's see. A biconditional is a special type of conditional statement that actually is true in both directions. So if Q, then P is true, and if P, then Q is true, and it's combined into one statement that has a double arrow. And a lot of times we read this as if and only if. So P if and only if Q. We'll see some more on this. The conclusion is the part that comes after the then. Usually we use a Q for that. Hypothesis, use a P. A conditional statement is an if-then statement. The inverse is the opposite of the converse statement. So we think of it as not P, then not Q. So if not something, then not something else. That's how we would form the inverse of the statement. The negation of a certain part is to add this tilde mark. So not P, not Q, basically inserts a not idea into the phrase. Contrapositive changes the position. So Q comes first and then P, and it also adds the not idea. So if not P, then not Q is the contrapositive form. A truth table is a way of evaluating these statements. So if the if part is true and the then part is true, we say the statement is true. A trick on this, though, is that if the if part is false and the then part is false, we still say the statement is true. We really can't make a judgment about the statement one way or another if the if part is false. So if the if part is false and the then part is false, we really just assume that the statement must be true. The converse form is to interchange the if and the then parts. So if Q, then P is the converse form. And truth value is basically like, is the statement true or is the statement false? So out of these, the contrapositive pattern you're going to need to learn, the converse pattern you're going to need to learn, the inverse pattern you're going to need to know, and also the biconditional pattern are all ones you're going to need to know. So you have to learn these patterns. Okay, let's move on. So let's look at this example here, or the explore reason rather. If-then statements show a cause and effect. The table shows some if-then statements. Determine whether each statement is always true or not necessarily true. So if it is raining, then it is spring. Okay, assuming that it's raining, it may or may not be spring. So this is a not necessarily true. Not necessarily, R-I-L-Y. Okay, didn't exactly spell that right, but not necessarily true. If x, y are whole numbers, then their difference x minus y is a whole number. This is also not necessarily true. Counterexample might be, what if y is bigger than x? That would give us a negative number, which is not a whole number. So if y is greater than x, it's not necessarily true. That would be, any of those would be a counterexample. Like y could be 7 and x equals 5. That would give us a -2 for their difference, and a -2 is not a whole number. Remember, whole numbers are 0, 1, 2, 3, 4, 5, and so on. There are no negative numbers. Third one, if water is heated, then it boils. Now this kind of makes sense, but if water is heated for some amount of time, then it boils. So this is also not necessarily true. Counterexample might be, water boils at 212 degrees. You could heat water and under a slow flame, and maybe it'll never get to 212 degrees because you got your flame down too low. You're heating the water, but it's not boiling. The fourth one of these, if a triangle has a right angle, then it is a right triangle. Now, there's only there's like 3 kinds of triangles we can actually think of. We can think of a triangle that does have a right angle in it. We can think of a triangle that has all acute angles, and we can think of a triangle that has one obtuse angle, and then the other 2 angles are going to be acute. And in all these triangles, the angles have to add up to 180 degrees. So they all have to sum up to 180 degrees. So one right angle, the other 2 angles have to be acute. One obtuse angle, the other 2 angles have to be acute. And 3 acute angles, all those angles have to add up to 180 degrees. So if a triangle has a right angle, it is a right triangle. This is true. So far, that's the one that basically is a true statement. Last one, if your favorite color is blue, then you're a good speller. We can see that spelling has nothing to do with what color you like. You may or may not be a good speller. So it has nothing to do with what your favorite color is. So this is not necessarily true. Okay, for the second part of this, write some if-then statements of your own. Write 2 statements that are always true. Now, always true, like this number 4 here is actually a pretty good definition for a right triangle. We're going to see that definitions are good starting places for writing true if-then statements. You just have to put them in if-then form. And 2 statements that are not necessarily true could be any 2 statements that you can make up. Like, if it is Wednesday, I am going to feed my dog. If it is Thursday, I am going to the post office. Anything like that. They may or may not be true, depending on, what you come up with. Okay, let's move on. Our essential question, how do if-then statements describe mathematical relationships? The if sort of sets up a condition that needs to be true, and assuming that it's true, does the result necessarily follow? And with mathematics, we can have a certain set of given starting facts, and from those facts, can we reason to a conclusion that is the then part of the statement, or can we come up with a counterexample? Okay, so here they're showing us that P arrow Q, P implies Q, or if P then Q. P represents the hypothesis, Q represents the conclusion. Okay, let's look at part A down here. You can register to vote if you're at least 18 years of age. Now here's the if idea in this statement, which means that this must be the then idea. Notice I found the if. So if you are at least 18, then can vote, can register to vote. Might be one way of writing the if-then conditional statement that goes with this. What do they do down here? If you're at least 18 years old, then you may register to vote. So get part B. Write each statement as a conditional. Okay, a square must have 4 sides. So we could say something like, if a polygon is a square, like they do here, so a square must have 4 congruent sides. Notice there's no if then, but if we're talking about a square, we could say, if it's a square, or if a polygon is a square, then it must have 4 congruent sides. Then it has 4 congruent sides. So we dug out the conditional of that. Now, I probably could have also done it this way. If a polygon has 4 congruent sides, then it is a square. And that would give a different statement it's actually the kind of the converse of this one, because the Q and the P are in opposite places. But that would be one that may or may not be true. Just because one form is true, like the original form here might be true, if P then Q, if P then Q, that doesn't necessarily mean that the Q then P version is true. Those have to be evaluated separately. Here we have a polygon with 4 congruent sides. Does it have to be a square? Well, this could be a rhombus. But if a polygon is a square, by definition, the square does have 4 congruent sides. So the initial form is true. The converse form is actually false. Let's move on. Okay, finding truth values of a conditional statement. Okay, so if the hypothesis is true and the conclusion is true, the statement must be true. If the hypothesis is true, but the conclusion is false, then the statement must be false. This is basically where we are looking for our counterexample. Assume this if is true, find a false then, and that makes the whole statement false. Now, if the hypothesis is false, we really can't evaluate the statement. But if the hypothesis is false and the conclusion is true, we have to assume that the statement is true, because the conclusion is true. It doesn't really matter about the if part. The conclusion is true, the statement is true. If the hypothesis is false and the conclusion is false, really the statement says nothing about the situation, so we just have to assume that it's true. So this is the one that is a little bit tricky to try to logically reason through, but if you just remember that if they're both false, then we just have to assume that the statement is true. It's almost like there's not enough information to say that it's false. Let's look at this one. Find the truth value. If a number is even, then it's divisible by 2. So let's say we pick a couple of even numbers like 2, 12, and -6. So here we have even numbers. Got this part, true. Are each of these divisible by 2? Yes. -6 divided by 2 is -3. 12 divided by 2 is 6. 2 divided by 2 is 1. 0 we could assume is an even number. 0 divided by 2 is 0. All those even numbers are divisible by 2. By definition, an even number is a multiple of 2, so it's going to be divided by 2. That means the conclusion is true, and from the truth table, a true with a true makes a true. So the statement is true. Let's move on. Example 2. If a quadrilateral has 2 pairs of congruent angles, then there's a parallelogram. We assume the hypothesis that it has 2 pairs of congruent angles is true. Let's see if it has to be a parallelogram. because if it has two pairs of congruent angles, then it must be a parallelogram, is what the statement is saying. We have they come up with an isosceles trapezoid as an example. Now, an isosceles trapezoid has exactly one pair of parallel sides, and the two, what we call the legs of the trapezoid, are congruent to each other, and the base angles are congruent, which means this angle down here at the bottom is congruent to the other one. And if we were to flip it upside down, those two angles here at the top would now be base angles, and those would also be congruent to each other. And this situation only occurs in an isosceles trapezoid. But here we have a quadrilateral with two pairs of congruent angles, yet only one side of sides is parallel to each other. So that's our counterexample. So using the truth table, the hypothesis part is true. We've got two pairs of congruent angles, yet the conclusion part is false. It is not a parallelogram, and that means the statement is false. We found our counterexample shows the statement is false. Let's move on. So here's sort of an overview of the different patterns that we've been talking about for making these statements. Converse flips the Q and the P. The negation just adds not. The inverse adds not to the P and the Q and leaves them in their original positions. And the contrapositive is like the converse with the negation added. You flip the order, so Q comes before P, and also you add the not idea. So if I had if today is Monday, then let's say Sunday is the first day of week, then second day of week. Let's say that's our statement, our conditional statement. The converse would be if today is the second day of the week, then it's Monday. The negation would be if it's not Monday or if it's not the second day of the week. The inverse would be if it's not Monday, then it's not the second day of the week. And the contrapositive would be if it's not the second day of the week, then it's not Monday. And so all these are variations of the same idea, but depending on the order and what your if is and what your then is, some of these may be false. Generally, we're going to see that the contrapositive matches the truth value of the original statement. So sometimes if you have an original statement and you can't figure out whether it's true or not, try to form the contrapositive and evaluate that. If it's false, the original statement must have been false. If the contrapositive is true, the original statement must have been true. Okay, let's move on. Let's look at example 3. We want to write and evaluate the truth value of a converse. So let's see what we got here. To write the converse, reverse the hypothesis and conclusion. So you play the trumpet. Let me see what they're doing down below here. The if part is if you play the trumpet. So I'm going to single underline that. It's hypothesis. The conclusion is you play a brass instrument. Here's the conclusion. Again, this is our P. This is our Q. We have P implies Q. If P, then Q. To write the converse, we're going to say if you play a brass instrument, then you play the trumpet. If you play a brass instrument, the conclusion part was moved up there after the if, and the you play the trumpet, which was the P, was put after the N. So we can see that the Q comes first, the P comes second in the converse form. Now to evaluate this as in terms of its truth value, let's assume that we're playing a brass instrument. So it's true. Now, are there other brass instruments than trumpets? We could be playing the trombone. That would be a false conclusion then. So, because a trombone is not a trumpet. any other brass instrument. Tuba would also be a brass instrument, but it's not the trumpet. So that would cause us to say that this statement is a false statement, the way that it's written. Let's look at example 4. Write and evaluate the truth value of an inverse and a contrapositive. Okay, if two whole numbers are both even, then their sum is even. So the hypothesis, if two numbers are both even, the conclusion, then their sum is even. So we want to evaluate the truth value of an inverse and a contrapositive. So if two numbers are both even, the inverse is if two numbers are not both even. If we want to form the inverse of the sum of two numbers is even, then we could say the sum of two whole numbers is not even, or we might say the sum of two whole numbers is odd, because sums are going to be either even or odd. The inverse would be if two whole numbers are not both even, then their sum is not even. And they note that the inverse is false. So if two whole numbers are not both even, so let's say we have a 2 and a 5, those are two whole numbers, they're not both even, they're going to add up to 7, then their sum is not even. It works for that one. Let's look at 3 and 5 though. If two whole numbers are not both even, so they're both odd. So if one is even and one is odd, it seems like it might work. But not both even means one could be odd, one could be even, or they both could be odd. Well, the case for both of them being odd, these two add up to 8, and that's an even number. And the conclusion of the inverse says that they're not both even. That makes this false. You've got true for the if part, they're not both even, but yet you have false for the second part. Their sum is not odd. Their sum is not, their sum is even. The conclusion would be their sum is not even. Let's look at the contrapositive. Now the contrapositive switches the order. So you have if the sum of two whole numbers is not even, then both whole numbers are not both even. So if the sum of two whole numbers is not even, then the numbers are not both even. Okay, the contrapositive is true. Whenever the sum of two numbers is not even, one of the numbers must be odd. Let's use 1 and 2. 1 and 2 adds up to 3. Here we have the sum of two whole numbers that isn't even, and the numbers are not both even. So we have a true hypothesis part, and we have a true conclusion part, which makes the statement true. Okay, let's move on. So let's talk about biconditional statements. Now, biconditional statements, I mentioned works both ways. The if P then Q is true, and also the Q if Q then P is true. They're both true. So we can write it in biconditional form with this double arrow, and we say if and only if. And sometimes you see it abbreviated as if with two F's. And there's no if to start it, there's no then, it's just something if and only if something else. So let's see what they have here. So if the original statement is true, So P if and only if Q is a true statement. If P is true, yet Q is false, that would be a false statement. If P is false, yet Q is true, that would also be a false statement. But if they're both false, then that means that we have to assume that it's a true statement from our truth table. When the hypothesis is true and the conclusion is false, this is where we find our counterexample. But if the hypothesis is false and the conclusion is true, that could also be a counterexample that would cause a statement to be false. Generally, though, if we have a biconditional statement is true, or you can't write it. You can only write a biconditional if it's a true statement. So if you see a biconditional form, if and only if, you're being told it's a true statement. Okay, let's move on. Write and evaluate a biconditional. A marine biologist writes this conditional: if a seahorse gives birth, then it is a male. Since it's true that among seahorses only the males can become pregnant and give birth, should the marine biologist take this as a biconditional in a paper she is writing? So a seahorse gives birth if and only if it is male, would be the statement. So let's see if we can write it both ways. Well, that's if it was true, we could write it both ways. We have to test it to see if we can write it as a biconditional. Does it work both ways? So if a seahorse gives birth, then it is male. That's true. If a seahorse is male, then it gives birth. This is actually false, because it may or may not give birth. It has to be pregnant before it can give birth. So here we have a case where one way P then Q is true, yet Q then P doesn't necessarily have to be true. This really cannot be written as a biconditional. It can only be written as a biconditional if it's true both ways. So for example 5, identify the conditionals in a biconditional. Okay, let's see. Triangle is equilateral if and only if it has 3 congruent sides. So triangle equilateral, 3 congruent sides. So one statement would be if a triangle is equilateral, then it has 3 congruent sides. The other one would be if a triangle has 3 congruent sides, then it is equilateral. And again, if it's written as a biconditional, it's a true statement, which tells us that each one of these statements must be true. If these weren't true, it couldn't have been written as a biconditional. Let's move on. Concept summary. If P then Q, if Q then P, if not P then not Q, if not Q then not P, P if and only if Q is how we would write those. Remember, again, in kind of an overview, if you can write this, it's always true, which means P implies Q is true and Q implies P are both true. These can be evaluated separately as to whether they're true or false. Okay, let's stop there.